We'll finish this section on expected value with a couple of games here. Now, let's suppose you were offered a chance to play the following game. I'll deal you 3 cards from a deck. If you get no face cards, you'll pay me $5. If you get 1 face card, I pay you $2. If you get 2 face cards, I pay you $10. And if you get 3 face cards, I'll pay you $15. So let's find your expected winnings. Okay, let's talk about the possible values of your random variable as far as your winnings are concerned. So you could lose $5 if you get no face cards. If you got 1 face card, you could win $2. If you get 2 face cards, you could win $10. And if you get 3 face cards, you could win $15. Now on this game, you don't pay to play, so we don't have to worry like we did with the raffle of taking money away from these values. Okay, now when I set up the table, I put an extra row up here just to show you what each of these columns represents, because remember, even though my random variable is the monetary values, these monetary values have the same probabilities as getting these number of face cards. So the probability of getting no face cards and the probability of losing $5 is going to be the same. The probability of getting 1 face card and gaining $2 is the same. The probability of getting 2 face cards is the same as the probability for gaining $10. And the probability of getting 3 face cards is the same as the probability of gaining $15. Now I calculated the probabilities of these earlier in an earlier example, so you can go back and look at that. But I found that the probability of getting no face cards was 0.4471, and so that's going to be the same as the probability for losing $5. The probability of getting 1 face card is 0.4235, and that's the same as the probability for gaining $2. The probability of getting 2 face cards is 0.1195, and that's the same as the probability of gaining $10. And then the probability of getting 3 face cards is 0.01, and that's the same as the probability of gaining $15. So now take these and multiply them. -5 times 0.4471 plus 2 times 0.4235 plus 10 times 0.1195 plus 15 times 0.01. And notice I get a -4 cents, or -$0.04. This means that me running this game, that I will average a profit of 4 cents per game. In other words, the consumers will average losing 4 cents per trial. Now it doesn't sound like much, but if I can get 100 people playing the game 50 times an hour, 24 hours per day, I will make a nice profit. And so this is how casinos get rich, letting just enough win to keep people coming. So in a casino, a game, on average, the average person may not lose that much per trial, but there's so many trials that it adds up. Okay. One more here. I thought I'd do this example of a roulette game. There's actually multiple types of roulette, but the type of roulette wheel I'm going to be using has 18 red numbers, 18 black numbers, and 2 green numbers. If you bet $1 on black, you get your dollar back, plus you win $1 if it lands on black. So, otherwise you lose your dollar. What is the expected gain to you in this game? Well, first of all, you can either lose $1 or win $1. And if you're going to bet on black, then the chances that you lose $1 would be 20 out of 38, because there's actually 20 places the little ball could land that's not black. It could land on the 18 red spots or the 2 green spots, so that's 20 places it could land out of 38. So the probability that you lose $1 would be 20 out of 38. Now the probability that you win $1, there's only 18 black spots that it can land on, that will win you money. So that would be 18 out of 38. So if you calculate the expected gain of this game, it would be -1 times 20 out of 38 plus +1 times 18 out of 38, and it turns out that that's actually -$0.05, or basically negative a nickel. So again, the average person would lose a nickel per trial. Again, it doesn't sound like much, but if you start counting how many times those wheels spin and how many players are playing per spin over a long period of time, then those nickels will add up. Okay? So I'll end with a little example here on warranties, because you probably know that you go into a store, you buy a new computer, you buy a new iPhone, you buy a new iPad, whatever. They always want to sell you that warranty. So let me show you this. Suppose I sell 10,000 computers, and let's say I talk 3,000 of those buyers into spending $129 for the second year warranty. Let's assume the first year it's warranty, but I sell them a second year warranty for $129. Well, 3,000 times 129 is $387,000. Let's say a repair generally costs the company $300. How many of those computers will need repair during year 2? Let's just say 500. Let's just say only 500 will need repair. Okay, let's say 100 of those people can't find their warranty information, so obviously they're not going to bring theirs in. Another 100 get fed up with the warranty process and just buy another computer. Now we're down to 300 people. Let's say another 50 do not get the computer in for repair by the deadline. So now we're down to 250 computers. So now it's going to cost us to repair these computers at an average of $300 per computer. It's going to cost us $75,000. Now compare that with how much revenue we brought in by selling the warranties, $387,000. So actually your warranties profited you over $300,000 for the business. So the business profited over $300,000 just on the warranties. Now, don't get me wrong, some insurance and warranties are important, especially on our health, homes, autos, etc. But some of these others depends on your point of view. So just like an iPhone, you can buy what they call insurance on an iPhone. Of course, again, if they sell insurance on all those iPhones to people, there's probably only a handful of those people that are ever going to use it, so they get to keep the rest of the money in profit. So anyway, this completes the section on expected value, and in the next section, the last section of probability, we do have 2 more sections left because one's on statistics, but the last section in probability I'm going to talk about has to do with conditional probability and Bayes' theorem.